Hi, my name is Franklin Aboto.
My name is Miguel Chataloy.
In this video, we introduced the first iteration of the FruiTREC agricultural robotics application for senior project of fall 2016. Our mentors were Dr. Wagner Vendrame, a professor of biotechnology at University of Florida's Tropical Research and Education Center, and also Leonardo Bobadilla, professor of computer science here at Florida International University's School of Computing and Information Sciences. Our instructors were Mohsen Tahiri and Dr. Masood Sajjadi. The project was motivated by researchers at the Tropical Research and Education Center, or TREC, who expressed a desire to be able to expand the scope of their research in agriculture. Specifically, they want to increase the size of the crops that they experiment with. Today, they use crops that are small and few in number. First, because collecting data by hand over large areas is tedious. The smaller the area of the crops, the more frequently researchers can survey them. Second, because it may be unsafe to survey very tall crops because of a risk of falling from a height. And third, because the cost of experiments increases with the number and size of the crops used.
So we set out to automate the process of data collection. Now we can't help with the cost of growing and maintaining exotic crops, but we can definitely help bring down the cost of manual labor required to collect those horticultural statistics the farmers care about. We do this by using an inexpensive aerial drone. We fly the drone along the sides of trees, recording video that later gets processed by our vision algorithms. The results of that analysis currently give the farmers an accurate yield count for the fruits their crops are bearing. Eventually, the goal is to completely automate the interaction between the human and the drone by achieving autonomous flight. Our system uses a client-server architecture pattern. The user interfaces with the client communicates with the drone over a Wi-Fi network generated by the drone. It sends commands to the drone and receives real-time telemetry and video streams. After a flight, the client sends the video to the server where it gets analyzed by the computer vision module.
The client should also allow users to generate and view analysis reports based on the image analysis performed by the computer vision module on the server side. In addition, we intended to create a website on which users could view reports with additional visualizations suitable for a large screened device, and also manage accounts and perform other tasks. To further introduce the project, we present a selection of user stories
over the network, or they can send commands to the drone to perform common operations such as taking off and landing, performing an emergency shutdown, and translating in three-dimensional space, such as going forward, backward, changing altitude, rotating. User story number 130, NavData Service Module. As a mobile developer, I would like read access to live drone nav data, such as altitude and GPS coordinates, so that I can use that information to make business logic decisions. The client device must be on the drone's Wi-Fi network as a precondition. The acceptance criteria is as follows. Must provide at least attitude, altitude, GPS, battery, accelerometer, gyroscope, magnometer, and fly state. All the nav data that is received by the device must come in real time. There must be no caching. So the way this is set up, the NavData Service Module sits between the network layer and the consumer in the Android application. For example, the user interface, which doesn't exist yet, but would consume the NavData service. The NavData service allows using a subscription observer pattern so that the consumers can call subscribe on any of the different telemetry statistics they want to receive, such as attitude, altitude, battery. And each of these emitters follow a very rigid class. So it's very easy to extend, to add something else, such as wind information. This is what it looks like when the drone is on and the device is on the same network. We're receiving the real-time nav data and we're displaying it on the screen as a test. You can see the yaw, roll, and pitch, and they will immediately change as the drone is rotated and moved in the air. The battery level and the GPS, two very exact measurements. User story number 223, Drone Control Service. As a mobile developer, I would like to be able to send commands to the drone via a module that abstracts the details of the network layer from my business logic. As a precondition, the client device must be on the drone's Wi-Fi network. My acceptance criteria is as follows. This service must expose 5 AT commands from the AR drone. ATREF, ATPCDMag, ATFTrim, ATCalib, ATconfig. These commands allow translating, changing the fly state of the drone, whether it's taking off or landing, collaborating the magnometer, collaborating the horizontal plane, and setting configuration. Another acceptance criterion is that the device must send an AT command to stall if no input is received for the drone for more than 1500 milliseconds in order to not lose connection with the drone. This is to get around a feature that the drone has that after 2 seconds of not receiving commands, it will terminate the connection. So we need to work towards that not happening. This is the general flow of what happens when a command is sent. Before we're even talking to the drone over the socket, we want to connect first. So the consumer will seek out the control service to connect over the socket in a proxy sort of way. This operation is synchronous. Once the connection has been made, the mobile developer is allowed to go ahead and send the first command. In this example, it's takeoff. And this is a method that exists on the control service rather than a AT command name. If the emergency mode is off, then the control service will fulfill that request. It'll instantiate a new command manager. The command manager will create a queue of commands, of AT commands, that it represents with this AT command class. And it will send in a separate thread one command after another over the data socket, serializing each AT command into the proper proprietary format that the drone needs to receive. And it's important to note that this operation, each command, is asynchronous. So the developer can say takeoff and then immediately say rotate, move forward. And while those commands have not all been fulfilled yet, they are waiting in a queue, and they will be asynchronously performed. This is a much better design than synchronously following commands, because then we run into the problem of not sending enough commands to keep the drone on, and even if we work around that, we waste crucial battery life and over user response time in queuing up commands themselves. We should leave it up to the business.
User story number 163. Design a website to view crop data. The idea of the website is to have a portable and convenient hub where the developers can test and view the post-processed data, and eventually be a part of the grower user experience. Since the core focus was to make a system as accessible, I figured a web-based platform could connect the user conveniently without having to worry about storage or system processing. Essentially, as long as they have Wi-Fi or internet connection these days, they can essentially go to the website and view their data. The acceptance criteria would be that it obviously communicates with the processing from the CV, facilitates the views of a typical SQL database, and obviously mobile friendly. User story number 175. Design a traditional database. Since the core of the project was tracking stats about crops, the necessity for a database was almost obvious. In this version, the big thing is really correlating yield count and time. The database is obviously tied to the website in order to mirror the info to the user's point of view. The acceptance criteria would be that the records are obviously updated per mission. You can obviously erase bad data, and obviously can organize the schema in whatever way. User story number 210. Generate graphs of crops. In order to make the stat tracking more user-friendly, deploying graphs to express the data seemed like a good idea. The graphs simply reflect the database in typical views like pie charts, bar charts, and line graphs. This can be escalated to reflect stats for different areas, like formal plots on a small scale or entire countries on the large. Essentially, whatever the user inputs, or essentially the developer in the area fields, would be the designated abstract or actual area. The acceptance criteria for this would be that the graphs would be generated in real time, same as the database, again compatible with the mobile, and the user can actually choose preferences of how the graphs would be styled.
Here's a selection of use case diagrams from the perspective of the algorithm engineer actor. User story 180. Design a segmentation pipeline for the brown Sapoti fruit. Given that the OpenCV and NumPy libraries are installed on the computer vision algorithm development environment, as an algorithm engineer, I want to create a segmentation pipeline specifically tuned to isolate brown Sapoti fruits in images. The number of blobs of pixels remaining after the segmentation should not over or underestimate the actual number of fruits in the image by more than 20%. You can see that in this user story, the resulting image after segmentation mostly contains pixels that are only associated with the Sapoti fruit. In the original image, one can see with one's human eyes at least 35 occurrences of a Sapoti fruit. The segmentation pipeline produces an image that contains only 23 Sapoti fruit. This is a 65% accuracy, which undershoots the desired accuracy of 80%, suggesting that a more sophisticated technique may be required. User story 213. Implement the histogram of oriented gradients feature description algorithm in Python. As an algorithm engineer, I want to implement a texture-based object detection algorithm to count fruits that are similar in color to their surroundings. In this case, we adapted an existing implementation of the hog algorithm and added utilities for constructing the data set that the SVM classifier would learn to classify from. It was possible to adapt an existing implementation of this pair of algorithms because for 5 years, from about 2005 to, let's say, 2012, for 7 years, this combination was the state of the art in classification of images. And so there was a wealth of implementations in many languages of this pair of algorithms working together. We adapted one by Mr. Hansra. And you can see we integrated the feature descriptor, which computes the gradients from the raw images, and then of course the classifier, which is trained to recognize the gradients rather than the raw pixels of the original image. User story 240. Create a Longan fruit detector using the HOG algorithm. Given that the HOG feature descriptor and the support vector machine linear classifier are both implemented in Python, as an algorithm engineer, I want to create an object detector specifically tuned to recognize Longan fruits in images. The detector's classification accuracy should be no less than 80%. This graphic illustrates the pipeline through which a raw image is pre-processed and then on which the processed image has detection performed. So in the top left graphic we have the input image. In the top center graphic we illustrate the pre-processing step of applying a bilateral filter, and the purpose of the bilateral filter is to smooth the regions of the image where effectively it smooths the entire image, but the objective is to smooth regions of the image where Longan fruit occur so that small deviations in the color, such as in the left occurrence of the fruit in that graphic, are sort of minimized, and you can see the effect in the right Longan fruit in that graphic, where the color is much more uniform, and it makes it easier to detect the fruits because once you apply this filter on all of the regions of the image where there are fruits, all of the fruits become much more similar to one another. And also all of the fruits become much more different from the other regions of the image that do not contain fruit, where high contrast is preserved and the blurring effect is not as strong, right? Because this is a bilateral filter, not a Gaussian filter. So edges are preserved. In the top right image, of the top right graphic, we show a scaling of the input image. And the reason why scaling is necessary is because if the object that we intend to detect covers too few pixels, if it's too small, then it will not be possible to detect the texture associated with that object. Right? The image has to be scaled to some minimum resolution so that when the gradient vectors that represent the rate of change in the intensity of neighboring pixels are computed, you can end up seeing very, very nice curved shapes, like in the bottom right of the gray image underneath the arrow with the title feature extraction with resize. Right? You want to be able to actually detect the occurrences of these fruits. So we apply a scaling operation, followed by, in the bottom left, the illustration of the execution of the detection algorithm, where for each of these small white windows, which are sliding across the image, one chunk at a time, one region of the image at a time, for each of them, we compute the gradient vector and then feed the gradient vector into the SVM classifier, which determines whether what it is seeing is Longan or not Longan. And at the end of the process, you get the bottom right image where we have a bunch of classifications, positive classification in the bounding boxes that are white, and then of course the negative classifications which are not represented at all. A related task is task number 242, in which we create training and test datasets for the Longan fruit detector. And you can see in color in the top left many samples that were hand selected representing this positive sample set. And then in the bottom right you have a bunch of black and white images which were generated automatically using one of the tools that you'll see in the installation and maintenance videos for automatically generating the negative samples in a training data set. We'll conclude with a view of our Burndown chart. You can see that around sprints 1 and 2, and also 3, the slope of the chart is relatively steep. I think that's attributed to the fact that we were assigning high point values to our user stories, given the amount of time that we were spending doing research and configuring our development environment and just becoming familiar with new concepts. I think that you see the slope sort of leveling off or becoming at least a little bit less steep around sprints 4, 5, and 6. And that's really because we were assigning fewer points to our tasks. Given that we had gotten some experience in the first half of the course, we could predict that we would make progress at a much faster rate. And so, that's illustrated here in the fact that it looks like we're progressing more slowly, but in reality, we're progressing more quickly toward the end because we are assigning fewer points. The Agricultural Robotics Senior Project offers inheriting students rich opportunities to showcase their existing skills and to develop new ones. If you like user experience and interface design, we've got client-side mobile development. If you're into web development anywhere on the stack, we've got that. If you like the science in computer science, we've got machine learning algorithms and applications. Everything is represented here. So far, we've accomplished piloted flight of an AR drone, an exploration of technologies for building web applications, including ones that are tried and true, like Postgres, and ones that are emerging, like GraphQL. And finally, we've explored and demonstrated techniques for performing object detection in images using computer vision. We hope that future students will achieve autonomous flight with the drone, more robust and accurate object detection given a much larger training set of images, and the establishment of communication between the client device and the image analysis module. Thank you for watching.